Okay, I'm going to try this again. Let's see. Alright, I apologize for that. It probably kicked everybody off. That was totally my bad. Let me double check a couple things here. Oh goodness. See, that's why I don't live stream. I'm not good at this. And let's just go into programming. Hopefully people can find their way back to the stream. And yeah, I screwed that up. I want to check one other thing and see if you can still get to the stream from the previous link that I had shared. Okay, it looks good. Sorry about that. So we're going to start with the programming, and if you missed any of the previous description stuff, I had to scrub it. So I'll just kind of cover some of the development process again as I'm going along here. So the code we're going to start with actually is something that I hadn't had time to really work on, but I was thinking about doing some basic routines to do super high res plotting. And this is kind of where I was at, where I had some routines to do simple things like clear the screen, set palette colors, and do some simple line drawing and single pixel plotting. And the thought was that you'd be able to call these from basic, essentially. And you know, really there are other basics out there. Excuse me, I need to take a drink. I don't normally drink soda. But I was sick a week ago, and my stomach is still a little upset, and I guess the carbonation kind of feels good. So I was going to implement Bresenham, or Bresenham, the line algorithm myself. And I'm sure there are other ones in the internet for 6502, things like that. So it's a pretty simple one. It just has sort of an error correction, as you're moving down the slope. And if you look online, I think I found one site. Yeah, is it this one? I found a site that actually, yeah, it had a couple of different examples of different languages, which I thought was cool because, if you wanted to implement this yourself, you could. But in my case, what I did was I knew that Andy McFadden had shared a really fast routine that was apparently kind of pulled out of some FTA code. And there's no real point in re-implementing it, especially for a fast one. Then this is really specifically coded for the 65816 and mindful of the 2GS's architecture. So I pretty much ripped that one out. There's not too much to it. I had to convert it from, I think it's in Orca style, to Merlin because I'm using Merlin 32. So let me move this back over. Checking the live chat. And let's start coding. So I was thinking we could do kind of a Christmas theme demo and maybe just draw a tree with this code. And let me first go ahead and open a new editor. I'm really a big fan of Vim, or VI for the editor, but for some things like being able to do global find and replace, it's nice to have a kind of a modern IDE because I'm not the best Vim user in the world. Okay. So what I've got so far, you can see a couple of source files over here. some macros, some GS routines that I typically use. GSplot is the actual file, and let me check one thing here. Actually, it'd be at the beginning. Yeah, so this is just actually assembled as a ProDOS 8 file. Okay, and I have a couple of equates here, which are 0-page locations that I believe are the basically, oops, the storage spaces for the lines. No, it's these, the CLP X0, CLP Y0, CLP X1, CLP Y1. So you can kind of see how I'm calling it here. I set the X0 and Y0 to 0, 10, and then 101, right? So if you were to look at that in sort of a coordinates way, it'd be like that, right? So from 0, 10 to something like that. Is that what I did? Oh no, I'm sorry. I actually store this 100 to both X and Y. So 100, 100, and then the last thing I do is I set the pen color to 1. And you can see up here above the actual palette colors that I'm setting. I'm setting an F33 to palette color 1 and 5F9. Looks like Michael Packard is here, author of the lovely Alien Downpour game, which I believe he still sells online. Hey, Michael. Okay, so again, kind of getting back to, I'll make this bigger. You really don't need to see this window. It's the output of my emulator. You know, I don't want it to be that fat that it wraps around, but for the sake of just seeing what my emulator has to say about things, I'll keep it kind of visible. Okay, so what my program does is it waits for a key. I'm going to take that out. It calls a super high-res clear memory routine. I'll show you that real fast. Really easy to explain. So I turn on 16-bit mode. I set these the accumulator to 0 because I'm going to store a bunch of zeros. I set X to 0, and even though it's 0 right here, really we're talking about a 16-bit word that looks like that, right? And the same with this one. Okay, so then I store it to the sort of native super high-res screen location on Bank E1 2000. If you're not a 2GS programmer, this 24-bit address is just the same as it's this, but you're saying I'm actually going to store it in a different bank. You get a lot of different banks to use. And it's kind of like the aux and main. You can use it the old school Apple II way, or you can do, 00 or 01 happen to be those banks if you are familiar with main and aux memory. That's where they are mapped on the 2GS. Okay, so I store it to this graphics location, and I just loop through for 8,000 times. This actually clobbers both the super high-res screen and all the scanline control bytes, which I won't really explain, and the palettes. So everything is zeroed out. Then it sets it back to 16-bit mode. I won't talk too much about the flipping back and forth between modes here, but I'll tell you when I'm doing it. So yeah, that clears the graphics screen, and on the 2GS, the memory, it doesn't do anything when you turn the graphics screen on and off, so you have to both clear the memory and turn it on. So I'll save this real fast. You can see the difference now. Oops, what did I do? Oh, sorry. I left my non-assembly in there. Okay, so now you can see it clears the screen, turns on super high res, and it just waits there. Give me one moment, please. I'm going to try and somewhat gracefully do this. So I'm sorry I had to Cough there, and hopefully I was able to mute it correctly. David asked if I could explain the significance of the direct page register to offset paging. So the direct page is really the same as zero page. I don't know if there's a... Sorry, I'm checking online real fast to see if there's a... I was looking for the WDC manual, of course, is the best place to really look at it, but that's really the only thing. It's the direct page is a zero page. What's different about it on the 2GS is like a lot of, well, like more things on the 65816, it's relocatable. So the direct page doesn't have to be at 00 anymore, and that's significant because it allows for things like GSOS to have multiple zero pages. And if you're launching from one program to another, you can basically say, all right, we'll give this guy a new zero page. We don't even have to stash the other one. We'll just leave it where it is. And that way you can kind of contextually, essentially have multiple programs running. Or, as in the case of GSOS, it's more about not caring ahead of time where it is. Direct page still has to be page aligned, so on 100 hexadecimal byte boundaries. But it's a really nice feature of the 65816. Another thing on the 65816 that's relocatable is the stack, which is used very heavily for what we call stack-based animation. There's so little memory bandwidth through the to the graphics memory because of a really horrible design decision that you try and do anything to write to it faster, and one of those tricks is to actually relocate the stack onto the graphics memory and just push effective values as fast as possible, because you can basically do an immediate push on the 65816 as well. So it's a lot of fun to program that processor. Okay, we'll actually try and type a little bit here. And you can see where I got here was I just started to do a bunch of sort of stubbed in quickie code. I'm not sure. Okay, I think what I was going to do here was do a single directional demo, like make a line that kind of bounced around. So I created some directional X, Y, 0. Let's first define what the somebody else commented on the design decision that I said was a horrible one that limits the graphics memory. It is. It has to do with some of the backward compatibility decisions. So basically it's locked at 1 megahertz, even though the rest of the system can effectively run at whatever speed that it wants to run at. So a stock 2GS is around 2.8 megahertz, but you're still only able to write to the super high-res display memory at 1 megahertz. There's some sort of caveats around that, but the even worse thing is that if you can try and do some things faster, it still has to synchronize between this switching back and forth between 1 megahertz and 2.8. So it's very unusual in that almost no 2GSs that run accelerators can be benchmarked the same way, because they're not always going to run at the effective same clock speed, because those synchronizations between the fast side and the slow side of the bus are not always reproducible, right? So anyway, somebody said they're not familiar with the 2GS. It has dedicated video RAM. Yeah, it's basically a linear frame buffer, and I can show you real quickly. Again, talking about banks, if you were to go into the monitor, you can type a number in slash, and all of a sudden you're in a different bank. So I just went into bank 1, which happens to map to the auxiliary memory on the earlier systems. And on a stock 2GS, the very first ROM 0 and ROM 1 editions, you got 256K. That was split into 4 banks. You got 00, 01, so there's your Apple IIe, or 2C, one of your later two versions. And then you got E0 and E1. And E1 is where our super high-res display is. So that is where we're going to work today. And just in case you're wondering, also on the ROM 1, the top 4, is it top 4? No, it's the top 2. I think it's 128K of ROM. So that would be up here in FE and FF. So this should, let's list some code. Yeah, this looks this is like real code, right? So, or, yeah, it looks real to me. I don't know. Yeah. So that's your firmware, actually. And then on the ROM 3, where you have 256K of firmware, and that includes a lot of Apple IIgs Toolbox, which is the sort of Apple IIgs firmware programming style. They expanded that on the ROM 3, so it goes down to FC, FD, EF, EF, F. Yeah. Anyway, good stuff. Sorry, excuse me. So I was thinking, let's draw a tree. Can I do that very simply first? And there's a couple ways we can tackle this. I'm thinking of a simple geometric tree using this line drawing algorithm. But if I were to do a more complex demo, I'd add some music and some animation around it. I don't think I'll have time to get that far. But I think we can at least sort of generalize one part of it, which is let's turn the tree drawing routine into something that we set the pen color and we call a drawing routine that we give a list of vectors to, and it draws that shape. So basically we're going to take what we already have, which is a line drawing routine, where I can pass in this x, y, x, 1, y1, and instead I want to be able to pass in a table that has just all of these values and then some sort of sentinel at the end, like a set of zeros, and that say just draw this, and then we'll go around. Somebody asked about the VGC mapping some spaces and not being able to do it from elsewhere. There's so much that could have been done. I think if the 2GS were really taken forward as a platform and they updated the VGC, what you see on a lot of platforms, even earlier Commodore 64 type things, is the ability to change where in memory these things lie, because really, I mean, you can see that's the super high res. If I could even just move it from 2000 to somewhere else, you could do some things like screen scrolling, right? That was a very popular trick, was to do screen scrolling by moving the memory by some sort of integral value that made the whole display shift, and then you could update chunks and then sort of do a big swap, but just bad luck, I guess. So if some electrical engineer out there wants to take over and build these things into a modern 2GS, I think it'd be really cool, but wouldn't be much of a market for it, unfortunately. Of course, if you were talking about those types of things like hardware scrolling through, changing the start of the display, another really nice option would just be to have sprites and real blitting, right? Okay, so I have some code here. I'm going to take this out. We're going to start with kind of what was up here. I'm going to take this out. This wasn't really useful. This was me starting a thought that I don't need to finish. And I'm going to leave this, actually. I set two colors right now. We'll just use this for our test colors. These are actually RGB values in the 12-bit, 4-bit per channel, but 12-bit color system of the Apple IIgs. You get it from 000 to FFF. So this is like a bright red because it's got a big F value, and this is pretty bright green. Yeah, there is actually a Super Mario Brothers for the 2GS. It's pretty decent. Lucas Scharenbroek does a great job explaining how to do stack animation and many other generic animation tricks to do pretty high-speed tile animation on the 2GS. So if you do look for the Super Mario Brothers on the 2GS, it's a great tech demo. Okay, I'm going to leave where I set all these colors. I have this is a test of a plot routine, so I can draw independent pixels, which is not something I particularly need in assembly, but but I was again working on this for sort of a library that I might use in BASIC. Let me do one other thing. I have version control, but I'm going to make a sort of backup of this. For a specific reason I may come back to later. Okay, I don't need this. I'm going to just comment it out for now. One other thing I forgot to mention is, I'll get into it when I start programming, is that I have a built-in code formatter, but I don't leave it running all the time. It runs when my build runs. So you'll see I don't indent things perfectly, and then later on they'll magically sort of indent. Okay, and you can see this is just two examples of the drawing routine, and then I switch back to, this is switching back to 8-bit mode, and all of that, and then there's another key weight, and oh yeah, another test of the plot routine. I'm just going to delete this for now. And it jumps to my ProDOS quit routine. Okay, so let me just make sure it still builds. And it should be decidedly less interesting, because I kind of just took out all the junk stuff there. Somebody said they posted this in the IRC channel. Yeah, there's IRC channel on irc.a2central.com. But if you check A2 Central, I believe that they have the IRC channel listed there. Okay. One moment, please. Okay. So let's start by kind of defining our function. You can see I have stuff down here, and I do Merlin assembly, so this MX tells the assembler that this is to be assembled in 16-bit mode, even if you know, it doesn't know, because I'm going to call it in 16-bit mode. And that's for all of these routines: SHR, plot XY color, palette index color. This is where I learned about that stack indexing that I mentioned a couple weeks ago on Facebook that I found very useful. Being able to add against stack values lets you kind of save a register. And we're going to make something that draws those sets of lines. We'll make it a draw list, and there's a couple of ways to do this. One is to have a table full of lines, so x1, y1, or sorry, x0, y0, x1, y1, right? And then do that over and over. Another is just to have all of the vectors, and it's going to say, oh, go from x0 to x1 to x2, x3. So the difference there is that you can only draw like a continuous line with the routine that does it the second way. With the first one, you would have to, you know, you have to define things a little more explicitly, but you're freed up, and that the lines can be arbitrarily anywhere on the screen. They don't have to be, so it depends on kind of how you want to batch your draw calls for your routine. And somebody asked if there was any relation to a shape table. I mean, it is a shape table. That's what we would be building. It's not the same format as the basic shape table, which is actually based on a bit pattern that says, you know, go up, left, right, or down, basically. and so in that one you can only make pretty specific movements. Alright, so hello Antoine, greetings, bonjour tout le monde en France. Let's do some actual coding now. I'm talking a little bit too much. For my table, I think initially I want to just be able to call it with a set of lines. We're going to draw a tree for our little Christmas demo. If I had more time, I would probably make it able to draw them somewhat randomly. So that I could have maybe more animation. So I'm thinking either way, the tree that I am trying to draw is closed. But you know, that's okay. I am going to set it to basically, here's the system we're going to use. And I can kind of set up a table for the tree right now. Trying to look up the format for hex. No, I think I will use... I'll use db or define byte. And we'll set it up as a list of lines, and we can imagine the tree sort of being formed in the middle of the screen, and the 2GS display is 320 by 200 display, so 320 on the horizontal, and the values that my line drawing uses are those actual integral values, even though they map a little differently in memory because you get 2 pixels per byte, right? So 0 through F, one of 16 colors. So we would still define the middle basically as being about 160. That happens to be one of my favorite hexadecimal numbers because it's AO, but I think I can do it with decimal numbers by dB without the $sign. Let me try this. So that would be the first X, and we'll start it, let's say 5 pixels down from the top of the screen, and that's the first Y, and then, you know, tree goes down like that. So I don't know how far we should move from that, but we'll start moving to the right here and just do it as, let's say, 190. So we're moving 30 pixels to the right and 30 pixels down. And we're just going to try and define that. Yeah, somebody asked if Apple tables or shape tables are only in AppleSoft Basic. Yes, real shape tables on Apples are an AppleSoft Basic thing. I'm saying more generically, this will be a shape table in the sense that I'm going to define my own shape in a table, right? Like, sorry, I'm not using the trademark version. I'm just using the generic term shape table. Anybody can make a shape table, so I'm going to make my own. Okay. Let me check one thing real quickly. What I want to double check is that my syntax is correct here for the dBs at the end. I'm looking at the output of the assembler, and I can't remember. Is this right? Okay, yeah, that's the line drawing. So let me find the tree in here. Yes, okay, so it did use my values as decimal values. It translated it from 160 to AO. Just wanted to make sure. Okay, so now let's make a function that we'll call, that we say, here's my shape table. Draw these lines. When you're done, come back to me. And I have these super high res things down here, so I'll kind of just base it off of something like one of these. In this case, it's going to be in the same bank that we're working in. I didn't talk much about the line drawing code that I took from Andy McFadden. That's in here is it actually uses another feature of the 65816 in that it is written for this bank, so it's not using long addressing. It's using essentially your traditional local addressing. You can see 2000, and what they're talking about is the graphics screen at E1 2000. So how does that work? Well, if you look at where is the actual draw line that I made? So I made a little wrapper for his code that does a couple of things. It goes to 8-bit mode and sets the bank. Well, it saves whatever current bank it's in, which in a ProDOS 8 program it's going to be bank 0, but this is really meant to be run as GS software. Then it sets the bank to bank E1. So this is setting the data bank. In other words, the 65816 is going to keep fetching instructions from where the current code is running from, but it's going to handle all of the reads and writes that you execute in whatever bank the data bank is. So basically you can write your code to run out of anywhere, but it's going to do all of its reads and writes here to the graphics display, which is great because you're not using 24-bit addresses, you're saving a lot of cycle time. That's why we do that sort of thing. Same thing with relocating the 0 page. Excuse me. So let me see. I set the bank for that, and I basically call his code. Yeah, so I'm going to do one that's called, whatever, SHR, draw lines. I would say draw shape or something, but really what we're drawing here is a table of lines, so it's going to be a line table, not so much a shape table. But and for draw lines, what would we need for our inputs? Just a pointer to the shape table, really. Since it's in the current bank, how should we do this? So I'm just going to pass it in X. We'll say that the pointer to the shape is in X. It's going to be a Antoine's got a really nice optimization, and I was just wondering about that. I'm going to go ahead and put that in real fast because it's worth doing. And I knew there was something that felt wrong about this. So you can see I switched to 8-bit mode, which you kind of don't want to do if you don't have to. But the problem here is not the PHB. If you look at the 65816 manual, this is always going to be an 8-bit push because the bank mode is only an 8-bit register, right? But I have to switch to 8-bit mode, so I only push one value onto the stack, because then I have to pull that off, and it's only going to PLB is always going to be 8-bit. So he had a right, like he's saying, B is always an 8-bit register. So what we can do here, instead of going into 8-bit mode, and this is a good idea. So you push your bank register, and then we can use the push effective address. Remember I said you could do an immediate push? And that looks like an address, but it's going to, yeah, sure it is an address. It's going to push E1 on there twice. So this is still our bank. And then all we have to do to even our stack again is pull the bank twice. That's a really great tip, Antoine. Thank you. Okay. And I don't even know why I did this. PLB is always going to be 8-bit there. I may have had some beers when I wrote that code. Let me double check that, make sure that I have not broken anything. Great. So now we're calling our draw line, and we just cut out a bunch of code. So really cool tip there for setting the bank register. You just learned from the pros, watching over my shoulder. Okay. So that is our test code. I'm going to leave that in there, and then I'm going to start on the tree drawing routine. Draw lines, sorry, that's what I meant. And, you know, I'm not sure which way to implement this. So basically, we need to be able to we need to be able to load from our table and call that draw line routine over and over and over until we hit the sentinel at the end, the zeros, the terminator. I'm going to go back to the tree. Yeah, I put in a... And we're going to actually need to change these to define word because we want 16-bit values. That's how we're going to pull them off and store them in the... is that what they are? I'd better double check. Yeah, these are word values. So you can see that they're spaced every 2 bytes. And that's how the drawing routine wants them. And we're just, it's, the drawing routine uses 0-page locations, wherever your 0 page is. In this case, since I'm doing this kind of in the, actually it's like Protoss 8 kind of emulation mode a bit, it's going to be the regular 0 page, not a relocated direct page. So what we need to do is take, you know, a routine that will go through this, and wherever it's pointing at this table, it's going to load these values and store it in the 4 values for our draw routine. Call the draw routine, and it doesn't stop until, I guess we would have to have all 4s zeros, because there could be something that starts at 0, 0 and goes to, you know, 100, 100, right? Like that's a valid thing to do, but you wouldn't draw a line to itself. Actually, you know, another way to do this for the Sentinel would be to do something like put in 8,000. I'm sorry, 16,000, whatever. You know, put in this so that you could just use something like a BPL or branch if plus or branch if minus, test on that high bit, because you would never have a value for a line that high, but you know. So let's see, do I do that? Yeah. We'll just say it's FFFF, right? And that's going to be our Sentinel now. Sorry it's taking so long to get there, but things will start getting faster. Okay, so now we know we're going to go through this, and, you know, on that first fetch from the next set of table values, if it's a really big value, we're done. You know, exit back. We've drawn everything in that table. And how are we going to call it? We're going to, you know, I guess since we're in this one bank, we could just pass it and use an index register because the table's local to us and everything. That's probably not, you know, the most elegant way to write proper 65816 code, but we'll get it written super fast. So watch out, y'all. All right, which register should we use? Let's say Y. Why not? Because I'm going to stash it anyway. Doesn't matter. All right. What would Y be? That's going to be basically the location of our table. Right? So we'll call it a pointer to our table. And what do we do in here? So we're in 16-bit mode. We've just been passed a pointer to the table. This is going to be really bad code, but all right. So what we have to do is we've got these values that we have to store all our stuff in. Sorry. And the table is x1, y1, or x0, y0, x1, y1. Right, so we're going to store in that order. What we do is, the first thing we do is start loading from our table in a loop. I'm going to start down here actually. And we don't know, where the table is. I'm not going to set a I'm not going to make self-modifying code or set a zero-page pointer because, I could just do it like this, right? They're passing in y the location of the table. Let's just load it. So what we would do is first check. We've loaded a value off our table. Is it a negative value? In other words, is a high bit set? If so, I'm going to just say we're done. And oops. Yeah, the autocomplete on here is totally crazy. Sorry, I don't have a great editor set up for this. Okay, and in this case, let's see. Range of minus done. We would, immediately store that value and kind of continue down the path here. So I think for readability, this is really silly. He wants me to put the start label. Hey, Antoine, regarding your comment on putting the start label, do you mean, can you explain that? Do you mean on this first line or on the first line of something else? Oh, okay. Yeah. So he's talking about a more graceful way to do this would be to put a label for the beginning of my program. Yeah. So the one problem with that is that, okay, all right, yeah, that will work. Sorry. I was thinking about the fact that this isn't GS, it's Protoss. So right here at our org, we can actually, can I put it on this line, Antoine? No. So you mean just like a regular pointer, right? Sorry, I was just trying to format that. So another thing I can do is just make it, just to kind of do all the build without running it. So just double checking that, yes, it recognizes start. So I was a little confused there because it's going to be, I'm trying to make this a little more generic than using LDA 0. It's not really good form, even though I could do it. So what we do now is use this for the offset because we know where the program starts. And I will add in, oops, wrong. And we can just, oops, yeah. And I actually already had a bug there anyway, because I wasn't indexing by 2 for word values. Well, that's awesome. There's a bunch of Super Nintendo and Nintendo devs or something seeming to watch this. I'm sorry, this isn't probably the best code you've ever seen. But that's the problem, you know, I never made the cut into Super Nintendo programming. I was just kind of getting good at assembly when the 2GS died. But hey, I'm learning, as you can see. Okay, so instead, what we've done now is change the code so that it's using this start offset, and we would, the only problem here is I still would have to call your routine. Okay, yeah. So I mean, there's a couple of things that I can do with this. Like, I was thinking that I could subtract the offset of our table and then call it that way, but apparently I was a bit correct in some of my previous assumptions about just kind of basing it off of 0. And we'll just set that back, but fix the addressing. And so I'm not familiar with this part of the syntax, but I'm being told that this is absolute. We'll just try and build it real fast. I mean, that's the thing. It's like, not to get all Bob Ross, but it's not bad to make mistakes, and that's why I'm not, you know, I wish this were faster for everyone's sake that's watching it, but code is just code, and you can rewrite it, so it's really, feel free to screw up. And a lot of times, like, I don't worry about the implementation because I may rewrite something 3 or 4 times before I actually feel like it's written the correct way for optimizations or particular use case. So what we've done now is base this on, yeah, happy little shape tables. So what I was being led towards is what you would do on a relocatable Apple IIgs program, is kind of base things off of, if you have data that's local to your code, you don't know where that's going to load on a System 16 program, and so you could use the start of your program as kind of an offset and then index everything off of that, which is in a lot of ways a lot easier, because I'm basically hard coding something here, but I'm doing that because in the ProDOS environment I'm writing 16-bit Apple IIgs code, but I'm really writing it in kind of the legacy operating system, and it's going to load into bank 0. I'm not going to take advantage of more than one bank for my code or anything like that, which I would do, and I'd probably do that next time. But I was playing with these routines for BASIC, so it was already in a sort of 8-bit shell, and I would love to do the same thing in 16-bit for a relocatable 2GS program, because you'd be surprised how easy it is to create a shell of one of those. And I have some examples of these different basic empty programs. If you are not a 2GS or Apple II programmer and you're kind of curious on getting hard started with programming, and you kind of, you know how to use an assembler maybe, but you don't know what an Apple II program looks like. I have this thing called gslib, and it's more focused on the 2GS, and I haven't finished it. But 3 important things in here are quit 8, and quit 16. This shows you how to build a simple binary file that you could load anywhere in memory. This shows you how to build a ProDOS 8 system file for an 8-bit program, or you can, as you can see in my case, you can do 16-bit code in there, and this is actually a GSOS like application that you would run, and they're super simple. They're just the skeletons. Here's what the GSOS one looks like. Like, literally all I'm doing is, you know, you set your data bank because you never know what things have been set to, and then you call the quit parameter. Like, that's it, but your code would basically go right here, right? So I have a very similar one for ProDOS 8. So if you wanted to get started, don't know where to start, ProDOS 8, you would do the same thing. And this is for the Merlin assembler, and I of course suggest that you use, if you want to do cross-assembly, to use the Merlin 32 assembler from Brutal Deluxe, available on their website, brutaldeluxe.fr. Alright, back to code. So yes, we're trying to make a routine that draws a little shape table, or in this case a set of lines. And what you're going to do is call it, I will use X. I don't know why I was using Y. It doesn't matter because we're going to have to stash this in between calls to the draw routine. So we would call it, here's our demo that calls this. We're just going to keep that so that we know that things are kind of working. And then a wait key, another wait key, so it doesn't just exit out after. And then we'll do our load the value into X. Oh, let me double check. Yes, all right, we're just making sure in 16-bit mode. That's with this reset processor. It sets the X and Y registers. I'm sorry, the index and accumulator word widths to 16 bits when it's in full native mode. So what I've done is load the 16-bit address now of tree. So if that's something like, if it's located at 2100, it's going to load into X, this value. And then we would draw. And it's going to do it in whatever pen color. It should return from that. And let's go look at that routine again. I haven't fully implemented it. So all I've done so far is load these guys and store them where in the 0-page locations that the line drawing routine is going to expect them. There are a couple of other things I have to do here. We haven't finished the loop. So it checks to see if it's hit a sentinel at the end, or the terminator, but we still have to increment at the end. We could do this a couple of ways. We could transfer X to A and do an addition. This seems a heck of a lot easier. So we've updated by X. We're always going to loop. And even though I don't have any code above this, I'm going to make a loop there. This syntax is essentially like an ephemeral label. It only exists within the last definition, or the last function that was defined. And I believe that when you look at the output of the of this particular assembler, it shows them remapped to just internally numbered functions. Just in case you were confused by that. Yeah, sorry. I have to use my smooth voice. I'm not trying to talk you guys to sleep, but I don't want to lose my voice. It's actually hard to talk for a long time. That's still alright. So much effort. I still say that this is. Oh, okay. Yeah. Sorry. Yeah, I guess I was off again. Gosh, I keep forgetting. I've been doing a lot of 8-bit programming today, and I keep forgetting that these are 16-bit words, and this would only advance us by 4 words, right? Or I'm sorry, 2 words. So, all right. Because we need to do a little bit more work than that, we're going to transfer X to A so we can do our addition. There's a couple ways. Typical way would be the, what are we adding? 8, right? Antoine likes this. Right, so this is 2, 4, 8. Yeah. Which to be fair, saves you cycles, right? I don't think it's as idiomatic to read, to be fair to myself, but you should probably always be able to map these types of things. Like I do use a lot of ASL and LSR. Somebody asked if about the flag, the hash flag that I use there to load tree, and I don't know if this is for all assemblers, but I thought it was pretty standard that the $sign typically refers to an actual sort of numerical value, and the absence of it would be more of a pointer. So if I wanted, the value A0, I would do it like that. Otherwise, this would be a memory address, right? And this even works for, in Merlin, if you want, you can do something like, what if I want to load A0, but I really mean I want to load a space. And this is an idiomatic, like I love this because this is a really great readable way to load a character value. So in other words, if you're a C programmer, this is, or other languages, this is kind of like dereferencing something. We're getting the address. So we're loading into X the location of tree. We're calling draw lines. Draw lines now is pretty close to done. What it does now is loads whatever is in the last line of the list, assuming it hasn't hit the end. At the end it increments the list and it loops every time. The only thing that we are missing is our call to the line drawing routine. I'm going to look back up here at an example that I had, the one we've been using, so we can see what it looks like. You have the pen color, and then you just call draw line. So there's really nothing else to it. Draw line itself does not look like it preserves anything, right? It preserves the bank value because it knows it's going to destroy that. It may or may not preserve these 0 page values, but as far as the registers, I'm sure they're all gone. So while this would be great, I'm sure this will screw up our loop because we'll probably lose everything. So I'm just going to store all of our main registers A, X, and Y. I already have a macro for that. And this is, this isn't necessarily efficient. I'm trying to do this quickly and not worry about whether or not I'm destroying my registers, so that's why I have routines like this. This may actually be the best way to write this code, but I could also go and look through and see what's really destroyed and what's not. Optimization is a fun game to play, but we're not really here for code golf today. Whoa. Alright, so I saw some really nice crazy stuff going on before that destroyed itself. And what happened is that I'm going to say it looped through this over and over and over. So let's do this. I'm going to take this code out that actually draws the line because I've clearly screwed up on the Sentinel or something. And here's a really quick way to debug it. I mean, I should probably go through this logically, but first things first, I will show you a really great debugging tip. Okay, so here's where we are. Oh, did I do? Wait key, I think, is 16-bit safe. But let me see. I don't know if I am even... Do I have a safe wait in here? No, I don't. Alright, so first of all, I don't think... I've done a couple of things correctly here. These should not be in in 16-bit mode. So, but that's okay. I'm going to take the weight keys out for a second. This last one is fine. And I still expect it to fail here. Okay. So it's a little different, but I think that's because it didn't do the weight key this time. So we've got that, and we just put in, I'm sorry, let me put in a break value. Breaks on the 65816 are quite similar to your regular break. So now we can step through it, and I just wanted to show you kind of GS Plus because I think it's an awesome tool. And I don't know if I can move it where you can really see both very well. Let me hide this. You can see here we are, LDX. Right, so that value is 2050, or sorry, hex 2050, not really. So let's see what that looks like. Actually, we don't need to do it there. Gosh, I forget the syntax in this one. All right. So 2050, and that looks right. So we've got our 160 and 5, and then what are some other numbers that I don't remember what they map to in decimal. So that's our tree table with the FF at the end. So it's got the right location. Let's continue stepping through this. So it's going to load that into X. Now we're here. So the first thing we would expect to get is our AO value. And we do. If you look up at the top here, sorry I can't put my mouse on the screen, there below the mouse it's got AO in the accumulator now. So it says BMI, which it's not going to because it's a small value. So it stores it at a 0-page location. Keep stepping through, right? And if I wanted to, I could go look at those 0-page locations using this cool memory inspector over here on the left side, but I'm just going to trust that that worked. That's not really an issue that I would expect. And then, so X right now, yeah, the ASL trick is not going to work for this, I don't think. Yeah, that's not what I intended to do with that. So let's just unobfuscate that a little bit, because it's a multiplication into, I'm sorry, ASL. I'm pretty convinced that drawline is still functioning as it was. Okay, and for the moment, I just want to do one quick thing. Kind of check where we're at with the build. Okay, so that looks right. We've got a line now in the center going down to the right. So let's expand on that and make a couple quick changes, and we can kind of wrap this up. So first thing is I have two pen colors here, a red and a green. I'm going to just set it to green for the tree part. And that's color 2. Okay, so now we have a green line, and we can go ahead to our tree and do this a couple ways. And you know, I would probably make some sort of tool that translates this from, you know, hand-drawn vectors or other vectors, but we're just doing this for kind of assembly glory. So really what we're doing here, we're repeating a lot of data. We're starting each new coordinates from the last vector that we ended at to, you know, draw a continuous line. That was a design decision that I made. Maybe not the best one, but I'm not known for making good decisions. So we're just going to move it back to the left. We come back in, I don't know, 10 pixels. So we'll say 180 and 5, and then we'll do the same thing. We'll step down and out by 30, so 210 and 65. So wait, did I do that right? No. That's actually going to kind of skip. Let's do it this way. I was close. I still need to start it at the last 190.35, like I said I was going to do. And then we kind of come into the sorry, I'll use the other hand movement. So you go down, then you come back in, down, in, right? So this might as well be a basic program, right? We're just sort of plotting these values from the 180, 35. Then we go down to what is it? 210 again, and 65. And step in again, 210, 65 to 200, 65. One more for a step down. Wait, that is the in, and then the down again would be 230 and 95. So this is a static table, right? And let's see. So we could have written this in another way to do some offsetting, and you could certainly add that into the draw lines routine, right? So another way to write draw lines would be to allow you to add a specific offset to each coordinate, and then you could all of a sudden be able to move these shape tables around. And I didn't do that here just because. So this last step down is, starting from the last point, 210.95 to 240, 125, and then we'll come back in this time almost to the center, to like, I don't know, 180. So we'll do 240, 125 to 180, 125, and then down. Sorry, 180, 125. It's just very confusing trying to talk and do these at the same time because I'm not so good at it. 190. Wait. No, keep the X the same. 180, 150. And at that point we would cross over. So we're at the bottom of the tree and we're going to go to the other side. We kind of need to invert on the other point of the 160. I'm going to keep the numbers even so it's going to be easier for me to track. So instead of 180 we're on the other side of 160, so we'll say 140, which, I'm sorry, we still have to start here at 180, 150. So let's just double check that the shape routine actually works, and it goes through a list of lines until it gets to the end. Oh, I missed a step. I did manual editing there, and it was looking cool for a second, but I messed up. So which one is that? That's, we got line 1, 2, 3, 4 lines right, and then I screwed up. So here we go. I came in, this should be 260. 65 to 230, 95. Darn it, I have to redo all of these. See, that's the problem of getting too far ahead of yourself. Come back in again. I'm sorry, 220, 95. And I know this part's kind of boring because it's not really programming, but bear with me. It'll be done shortly. Wait, keep doing that. That should be down to close to the last two lines, which will still be off. Okay. And I don't need to come in a little bit. I need to come in a lot. So come in all the way to 180. And then we do 180, 95 to 180, 120, and 180, 120 to 140, 120. That should be a little bit better. Okay, so we've got kind of our half of a tree coming back up. It's going to be the opposite of this. 140. Alright. I don't know if that makes sense because I'm kind of going in the opposite direction, but it's just easier for me to steal these. And so 140, and this is, what's 230 minus 160 is 90, so that's 160 minus 90 is 70. Let me make sure I have my math right. That's how bad of a programmer I am. I'd rather just kind of check it. Oh, and it's wrong. Whoops. Okay, what did I do? I'm sorry. I have a barking dog in the background. That's not distracting. Sorry, I was at 140, 95. Let's do it this way, coming back up. Oh, that's what I did. So I'm just going to actually go down the left side. So we'll do a slight offset, I think, because otherwise our line will show some weird aliasing errors. So to keep it synchronized, but to keep the numbers together, well, let me see what it would be. We did 165 here, and then we went... No, that's the same. We can do it the same way. We'll fake it. We'll fix it in post. Okay, so we're going down and to the left, which is going to be, 130, 120. No, sorry. 130, 35. Same thing. Oops, 140, 35. Sorry, 130, 35 to 140, 35. I know, we'll all be glad when this is over. Okay, so, and then 40, 35 to 110, 65. Oops, 110, 65. Gosh darn it. To 120, 65. 120, 65 is going to be the last step down of our tree, which is 90, 95. And then 90, 95 should be the guy that connects to the stem, but we go all the way across to, what is it? Not 160, I think we're back at 140. Double check that. Okay, last thing. Coming up, or sorry, down from 140.95. Where did we end up over here? Came back across, didn't we? To 140, 120. Okay, so we have our tree. That's, I guess, all well and good. It seems like not the coolest demo per se. There's a couple of things we could probably do to make that a lot cooler. Let me take out the test code real fast. A real quick one that I could do would be to, like I said, make a different drawing routine that lets me call the draw table. Another idea I had for this would be to set palettes of different colors and draw a lot of trees, you know, across the screen, or even keep a table that stores what past positions were, so I could draw them and kind of fade them out as new ones are being drawn. Let's do a quick test here. One other thing. We'll do this. Sorry, I don't have a quick switch between. I don't have a safe 16-bit weight here. But just for testing this, let's do this. And then we go back to 16-bit, full 16-bit mode. Well, actually, I don't even know that we need to do that. Let's do it this way. And hopefully this isn't too annoying for anybody to see, but what I'm going to do is draw it between the two different colors, green and red. So you see I just changed the pen color, and then I call my draw lines routine again. And we're going to do that in a loop. We don't need this. Oops. And why am I doing this? Because we're going to see how fast it is. And let's set the speed to 1 megahertz. So this is at the actual Apple IIe speed, not a native GS speed. And you know, I don't know if you can tell, but it's actually quite fast. Like at that point, it's so fast it's kind of doing a weird strobing. But this is not slow code. So you know, I would really love to do more. In a weird way, we kind of got a little animation effect just by drawing that back and forth in two colors. But my point is that the code for the actual line drawing is not mine, and it is quite performant. You can find it at www.fadden.com. He's got a lot of great code there. Most of it I haven't checked out. You know, if you're interested in doing a Bresenham, or I don't know if it's Bresenham, there's kind of two possible English pronunciations of that name, but I don't think it's worth optimizing the code in the way that you would need to come up with one that is this fast. You know, and it's doing a lot of things here to try and be fast, because if you remember, I mentioned the 2GS display is 2 pixels per byte, and so that means that if you're working in native 16-bit word size registers, that's actually 4 pixels per word, and that gets kind of hard, right? So you're trying to draw single pixels, but you have to do it with a word, so you can see there's a lot you kind of have to do to figure out where you are on the sort of pixel offset and then map that. And it's a great exercise to do, but I would highly recommend you check out that source if you want to do it. And then in my case, all I did was write a little wrapper routine. Again, I've been a bit sloppy here, but this is, obviously not meant to be primetime code. You can see some other stuff I have in here, like in the case of the drawing routine, it's using adds because it's going to add as it works its way down on a line. For a lot of my routines, I'll use a line table that just has all 200 lines of the super high res display prepared to be used from this table so that you can load offsets that way. Just depends, there's no wrong way to write assembly if it works. Kind of being tongue-in-cheek there. Sorry if that was boring and didn't do as much as you thought it would. Let's take one last look at our awesome demo, and let's put it in 8 megahertz. Whoa, flicker. And there we go. As fast as possible, it almost looks like a string of lights. So one of the reasons I wanted to do the work with the Bresenham is because it was always a dream of mine to get properly working line drawing routines when I was a kid, and I found it like just very heady stuff. And even though I can write my own now, it's really great to just have some code that you can call with, hey, this is what we all want to do when we're drawing a line. We just want to give it the coordinates, call a routine, and be done with it. So I will, maybe at some point try and clean up and share a bit of a library that can be called either from BASIC or somewhere else. But this is a weird mix, a hodgepodge of styles of sort of like I said, the legacy OS environment with a mix of 2GS and 65816 16-bit code. And that's all. I'm gonna leave it there. And again, I will eventually try and get back to doing prepared videos, but they take so much time. But the difference is you don't have to see me stumbling my way through it so much. So really appreciate everybody's time. Happy holidays. Get out there and program if you got a little time. I'd love to see what everyone else is doing. I'm always encouraged by the incredible people, not just in the Apple II community, but all of the retro enthusiasts. And of course, I'm a huge fan of the 6502 and 65816. So everybody keep up the good work, and have a lovely week, and we'll see you back on the internets. Bye-bye.